Okay, so today I want to tell you about lower bounds for read-only Oblivious RAM. This is joint work with Daniel, and I borrowed some of his slides. So I know you've already seen Oblivious RAM, but just to kind of remind you and set notation and so on, so what are we interested in? Oblivious RAM, ORAM, introduced by Goldreich and Ostrovsky in the 80s and 90s. We have a client. The client has some large database or virtual memory she doesn't want to store locally. She wants to delegate it to a remote server. The server is going to store it in physical memory, and the client is only going to store a small state. And after this setup phase, the client can access the database, so read from it, write to it, while hiding everything. So hiding whether she's reading or writing, which location she's accessing, and what she's writing into this location. And this should hold even if the server is maliciously corrupted. So this means that the physical access pattern, the actual access you make to the memory on the server, hides the access pattern to virtual memory. In particular, if you want to read one location, you might perform several operations on the server. You might even write to the server, even though you're not writing anything to your actual virtual memory, just as preparation for future operations so that you can preserve obliviousness. So of course, a trivial way of doing this is just every time the client wants to access the database, the server will send everything over, she'll update the database, send everything back to the server, which would be awful. So a really important efficiency measure for Oblivious RAM is its overhead, which is the number of physical accesses you need to perform to emulate one virtual access. And there's been a lot of work on this ever since the first Oblivious RAM paper, which obtained a scheme with log cubed and overhead, where n here is the database size. And this was later improved, culminating at works called pathoram and circuitoram, which obtained log n overhead. But with a caveat, which is that they obtain this overhead if the virtual memory has a sufficiently large block size, which is the basic unit of the virtual memory of the database. And then recently, last year, in two works, this caveat was removed. So finally, we have this work from last year called Optorama, which obtains log n overhead with no caveat. So it's called Optorama. So what do we know about lower bounds? So unfortunately, you know a lot about what we know about these Oblivious RAM lower bounds. So what we know from the original work of Goldreich and Ostrovsky is a log n lower bound. And it's pretty strong because it works even if in very restrictive settings. So for example, even if your database is static, you only read from it, you never update it, still this lower bound holds. It holds also in an offline setting, which is extremely weak, where the RAM program has to specify all its accesses in advance. So it needs to say which locations it's accessing, whether it's reading or writing, and what it's writing. And I say that this is extremely limited because, for example, you can't implement binary search there or other very basic algorithmic tasks. So this lower bound seems really great. But it has one caveat which makes it somewhat restricted. It only works for schemes that have a specific way of, in which they operate. And this is the balls and bins model, which basically means you have no way of encoding the virtual memory. You just take the database blocks, the data blocks, you think of them as balls, you put them in bins on the server. What can you do? You can move them around, but you can't do anything other than that. So true that most Oblivious RAM schemes that we know work in this model, but still this says nothing about general schemes. So the main open question left open by this work in terms of lower bounds was, what can we say about general schemes? Do we have such a lower bound? And this question was revisited by Boyle and Naor a decade later, and they show that such a lower bound is unlikely to exist if you restrict yourself only to the offline setting. So in what sense is it unlikely to exist? They show that if you start out with very, very small sorting circuits, so little o of n log n, you can get an offline ORAM scheme with little o of log n overhead. So defeating this lower bound if we have these amazing sorting circuits. Okay, so this result, I find it very interesting. Like, you might think, I think this was the thought in the community, that this lower bound holds in general, even though it was proven only for balls and bins, the Goldreich-Ostrowski lower bound does hold for general schemes. And here, this Boyle-Naor puts a dent in this, kind of belief that we have as a community. But it only works for offline ORAM schemes, and what we care about are online schemes, which don't, online programs which don't have to state everything in advance, all their accesses. So last year, in a really nice crypto paper by Larsen and Nilsson, they proved that yes, there is an oblivious RAM lower bound for general schemes, not restricted to balls and bins, in the online setting where you support reads and writes. And both of these are inherent to their result. So if you remove the online, we have the Boyle-Naor lower bound to a lower bound. And if you remove the ability to write to the database, then their proof fails. Like their proof uses the fact that you can update the database. But what happens? Maybe if you're only interested in a static database that you read from, and there are many applications where this is what we care about, maybe we can get something which is little o of login overhead. And this is what this work is about. We're revising the question and asking, is there an oblivious RAM lower bound for online reads for general schemes, not restricted to balls and bins? So what we show is a lower bound to a lower bound. We show that such a lower bound is unlikely to exist if we're talking about read-only ORAM, online ORAM schemes. So in what sense is it unlikely to exist? In the same sense as the Boyle-Naor result, what we do is we take these amazing primitives and we show that if we had them, we could get a read-only online ORAM scheme with little o of login overhead. So what are these amazing primitives? So first, sorting circuits, just like Boyle-Naor. And the other primitive is locally decodable codes with very good parameters. So with small query complexity and short code words. So I'm going to say more about these codes later on. For now, just think of them as these two primitives that we use. And what do we need from them to get little of login overhead? Well, we can use different parameter regimes, and we would get different types of overhead in our scheme. So for example, you can go for something that seems really great, like the dream, perhaps, oblivious RAM, where you get log n overhead. So extremely low overhead. You need to start with really, really amazing primitives. So what do I mean by really amazing? The sorting circuits should have linear size, and the locally decodable codes need to have constant query complexity and polynomial size. So I didn't tell you what these locally decodable codes even are yet. So maybe it doesn't, you have no intuition of whether we should have these or shouldn't have these codes. So what do we know? We don't know how to get these codes or these circuits. But we don't know how to rule them out. And in complexity theory, people have been looking at these types of questions for a while now. So for circuits, you know that proving lower bounds for general circuits, not specifically sorting circuits even, is notoriously difficult.
So just a question, it's unlikely to exist or it's unlikely to be proved unconditionally? So the lower bounds probably...
So I'm going to say a little bit later about how to interpret this, but I think it depends on your point of view. We don't know. So it depends whether you think that these primitives might exist, and then you won't have a lower bound, or you think they might exist, but we won't ever be able to say anything about whether they do or they don't. Yeah. So it's sort of but I'm going to go with a lower bounds perspective because it's a lower bounds workshop, right? Okay. So what do we know about LDCs? So they have been studied in a really narrow type of parameter regime. And we can make do with a much wider range of parameters. So for specifically in the coding theory community, they've been looking at binary locally decodable codes and really, really small query complexity, so constant query complexity. So we can make do with polynomial size alphabet. Doesn't have to be binary. We can make do with polynomial size code words, any polynomial as large as you want. We can make do with any constant number of queries, again, as large as you want, and still get this amazing log n overhead. So what we know in terms of lower bounds is only something which is slightly superlinear. And this is for binary codes. So what happens when you go to quadratic or square n or whatever, we have no idea. These codes might exist. What do we know in terms of upper bounds? So again, this has been studied in a really low query regime. So 3 queries, we have something which is sub-exponential in length, in the code word length. So there's a lot of wriggle room in this, in between the lower bounds and the upper bounds.
I'm not sure that it was not studied. I just think that whatever they know how to do, they were able to bring it down also. I mean, I think there's like a 6-query locally decodable code, which is
a what?
slightly 6-query locally decodable code, which is like sort of an easy way of looking at these 3-query things.
They achieve the same thing, right? So they all look at really, really low query complexity and binary.
There's 2 things. One, what is they achieve and what they looked at. I mean, I think that in the literature, like it's going to be like a big, like an open problem that people really would like to solve to get with any constant query complexity and anything smaller than what is currently known. Which
I agree. I agree, but I think the focus has been on this 3 query specifically. This is my understanding of it.
You need the alphabet to be binary?
So okay, so for the lower bound, it's for binary alphabet. For the upper bound, they obtain a binary alphabet, right? So I No, we don't. That's exactly what so let me stress. We can get a polynomial, you can use a polynomial size alphabet, right? So huge, like what can we do there? God knows, you can do many things when you allow a really large alphabet, right? And this has no effect on our result. Okay. So how do we interpret this lower bound? So Muhammad asked before, well, it depends whether you're a pessimist or an optimist. You can look at this as indication that we're never going to be able to prove an Oblivious RAM lower bound for online reads, or as motivation to study these primitives. So I personally am not looking for to construct these like very small sorting circuits, but maybe someone in complexity theory is and motivated by this result, I don't know. But again, no, for this workshop, it's lower bounds, no positive side to it. Okay, so what about going beyond read-only? So you should kind of be very worried now that I say this, because we know what happens when you go beyond read-only. You have a log n lower bound. So what do I even mean? What I mean is think of a scenario where you have a database which you don't update very frequently. So basically, you update it once every year. So you really want very low read overhead. You're OK with any non-trivial write overhead. In particular, you're OK with revealing whether you're doing a read or a write. So again, if you update the database at certain periods of times that are fixed and known to everyone, who cares? Like, you reveal the fact that you're writing, everyone anyway knows that you're writing. So in this setting, we extend our result to get little of log n overhead and enter the epsilon write overhead for any arbitrarily small constant epsilon. So in particular, starting with the same amazing primitives we did for the read-only scheme, as well as one-way functions, we can get the same read overhead, log n, with n to the epsilon write overhead. Okay, so there is a fine print to this result. I kind of glazed over this restriction, this caveat on the block size when we discussed the upper bounds. So what is the fine print? It's that in our construction, there's a discrepancy between the basic unit of memory on the client, so the virtual memory, and the basic unit on the server, the physical memory. So the physical memory blocks are much smaller. We call them words. They consist of W bits. On the client, we have larger blocks that consist of polylog B words. And for us, a word is log n bits, and a block is polylog n bits. What does this give us? It gives us more flexibility when we operate on the server. On the server, you can access a polylogarithmic number of words while you're basically only morally accessing one block. But you can access them in any location that you want. You have flexibility in how to access them. You don't have to read them block per block. So now we need to kind of revise what overhead means, because we have different basic units. So now overhead is going to be the number of physical words you need to access on the server per one virtual access divided by the block size. So basically, what you would expect the overhead to be, this is the new definition of the overhead. So now you know everything. And this type of assumption on the ratio between the block and the word size is the same as was used in pathoram and circuitoram and so on, the previous constructions. Okay, so now I want to kind of tell you a little bit about the construction itself. So I'm going to start with what these, yeah.
So just for this read versus write, this, Casper and Jesper low bound, it critically use both reads and write, but if
Yes.
you use the fact that you cannot tell read from writes, or just that you can do both. So in other words, with the low bound hold, if you know where was the reads are, where was the writes are, but you don't.
It uses the fact. Yeah,
So-
because you move from access pattern where you write, random stuff, read, random stuff, to mixing and matching, write, read. So you really have to not know whether you're reading or writing.
So, is it still then open if, for example, you are happy to tell when you're reading and when you're writing, what is the status? And what do you believe? So if, right, because
so you need to be more specific with the parameters, because our construction achieves a different.
Worst case you don't like to end with epsilon log n. If I want to define worst case overhead, both
Like log, and log?
so Zaproban gives you log for both, but for example, is it conceivable, for example, to have log n overhead for both, for example, under this, if you're happy to reveal the pattern? What's this?
Actually, you might be able to get log for both without revealing the pattern even. I don't know.
No, but I thought cabinet approved that.
I remember he said something.
So even for differentially private access pattern, if you relax that, he was showing that, you can't reduce both of the same.
Oh, I see. So maybe there is a reason.
So I don't know. I'm sorry. Okay. So for the constructions, after I explain what locally decodable codes are, I want to show you our read-only construction. Unfortunately, I won't have time to say anything about writes. I'm going to start with a scheme that doesn't really get what we want. It gets us to a bounded, it's going to be oblivious for an a priori bounded number of accesses. And then we're going to remove this restriction. But we're going to start with locally decodable codes. So what are they? They are error correcting code. They map n symbol messages to m symbol code words. And I'm denoting the locations color coded. So the first location is red, the second is purple, the third is orange, and so on. This will come up. So in what sense are these locally decodable codes locally decodable? In the sense that there is a decoder that can recover any specific message symbol that you want by querying only few locations, k locations of the code word. And we're going to need another property from these locally decodable codes, which is called smoothness. So this means that if you look at each of these decoder queries in isolation, it looks uniformly random. Of course, when you look at all of them, they encode the location you're trying to recover, but in isolation, they look uniformly random. Now, as I said, we can use different parameter regimes, but for simplicity of this talk, think of this best case scenario setting where the query complexity is constant and the code word length m is polynomial.
And it's okay for you to have constant error? Well, I guess, so the probability of being correct is like 3/4 or something?
So you would amplify 3/4 would not be enough to get negligible because you would introduce a log n overhead.
Okay. But for your result, you need like almost perfect, right? I mean,
So we talk about perfect, you can relax it, but not to constant, because then you get log n over it.
So you need negligible error.
Yes, or super polynomial, yeah. Okay, so now for the bounded access scheme equipped with these locally decodable codes, here's a thought, an initial idea. We know that you can recover, if you take your database and you encode it using a locally decodable code, you can recover any database entry by only making k queries. And these queries, each in itself looks uniformly random, but when you see all of them together, you know what you're trying to recover. So let's store on the server k copies of the locally decodable code encoded database. So we encode the database, we store k copies, we permute each of them using a uniformly random independent permutation. Now we know how to decode, so what you do is you run the local decoder, you get k queries, you send each query to a different copy, you permute each query using the right permutation, right? So the first permutation to the first copy using the first permutation. So this gives us correctness. You can always recover. What about security? So what does the server learn? Basically, the server learns when you're making repeated queries to a specific copy. So for example, if I'm making I1 twice to the first copy, I'm going to query the same location. I'm applying the same random permutation to it. But if I'm making two different queries to this first copy, the permutation is going to send them to completely uniformly random locations. I won't know anything about the connection between them. So said differently, if I never repeat queries, to each code word copy, all the queries I send are fresh, the server learns nothing. Okay, so this gives us a way of kind of revising the idea to make sure that queries are always fresh. So as before, we're going to store these k code word copies permuted. We're also going to store for each location and each copy whether it's fresh or not, whether we've accessed it or not. Now the client is only going to make fresh queries. So you run the decoder, maybe you get a query that you've already queried before. So the first query you've queried to the first code word copy. Okay, run again. Okay, maybe again you've hit now the second query, you made it to the second copy. Okay, run again until you get a fresh set of queries. And then you can make it as before, make these queries, get the response, and decode. So in terms of, now we have these like, is it fresh or is it not fresh? How do we keep count of this? This is metadata. It's much smaller than the data. It's 1 bit per entry. So we're going to store it on the server. What exactly am I going to store? So I'm going to store for each copy, for each location, each copy, whether it's fresh or not, 1 bit. Another thing I'm going to store on the server is the permutations. So I kind of never specified how the client knows how to permute. So I could use pseudorandom functions, for example, but I want information theoretic security for this. So I'm going to just store the permutations on the server. Again, it's log n bits per block. If the blocks are large, this is nothing. So in particular, I'll show you later that you can store it in any polylog overhead oblivious RAM, read-write oblivious RAM. So I really don't care which ORAM you use to protect the queries, the accesses into the metadata. So this is the entire construction. I have the code word copies. They're permuted as before, and I store the permutations and the freshness bits in an ORAM.
So your construction ends up being statistically secure, yeah?
Yes.
So even ruling out statistical requires lower bound, which is a strong one.
Yes. So for the writes, when you support writes, you either get computational security or you need another assumption on the code, which I think is pretty mild. So for example, any linear code satisfies it. Okay. So in terms of security, we get it for free in some sense because all the queries now we make are uniformly random. We never repeat a query, and the permutations, the random permutations, make everything uniformly random. What about correctness? So why would things not be correct? So the problem is the client can only make queries when they're fresh. Yes?
You don't understand the model, so do you have like a random oracle? Like where do you get the, how do you do the encryption and the setting?
So, okay. I didn't go into this. So in what sense is it statistical? When you have this hybrid model, or idealized model where you think the server only sees the access pattern, doesn't see the actual contents of the memory. Then you get statistical security. Of course, to implement this, you introduce computational assumptions to do the encryption, but it helps you separate where like in Alessandra's talk, where you have the information theoretic and the crypto, it helps you separate what's information theoretically secure and what's crypto secure, okay? Okay. So, can the client always find a fresh set of queries? Well, if he can't, then we don't get correctness. So this is where we get the bound on the number of accesses. The truth is, if you make too many accesses into the database, at some point you won't be able to find fresh queries. But if you only make how many queries, so basically code word length divided by twice the query complexity, if this is the number of accesses you make up to this bound, then you will always be able to find a fresh set of queries after, let's say, trying for log squared number of times. And the reason is the smoothness of the code. So each location in itself looks uniform, so you can do kind of like a union bound and show that you would, after sufficiently many trials, which is polylog many trials, you will be able to find a fresh set of queries.
And what happens after you give the route?
I don't, because this scheme is bounded access. Okay, for now. In a moment, I'll show you what happens after. Okay. What about the overhead? So now we're accessing this metadata, but the saving grace is the metadata is, as I said, much smaller. So it's so small that you can afford polylog many operations on the metadata, and still this would only count as accessing one block. So in particular, I can store the metadata in any polylog overhead Oblivious RAM, and all the cost of the metadata is just a constant number of accesses to blocks. So overall, I would get, if I start with constant query complexity, I have to access a constant number of blocks. So this is a bit more general than that. If you start with a smooth LDC that has a k-query local decoder, you get a read-only ORM scheme with order k overhead, which is secure up to code word size divided by twice the query complexity number of queries, number of accesses. No sorting circuits, just LDCs. But this is not what we want, right? I mean, I don't know how many accesses I want to perform into the database, so how do I move from a bounded access scheme to an unbounded access scheme? So what happens after I exceed this m over 2k bound? The client might not be able to find fresh sets of queries. I have too many correlations between the queries. So I need to break the correlations. Basically, I have to replace the permutations. Once I choose a new permutation, who cares if queries are fresh or not? I'm applying a different function to them, so I'm starting afresh once I replace the permutations. So what's the idea? The idea is to take the execution and divide it into epochs. Each epoch is the maximal number of queries, of accesses that I can accommodate. Once an epoch ends, I'm going to replace everything. So the client will choose fresh permutations and repermute all the code word copies using these sorting circuits. And this doesn't have to be, like very, very fast operations. Then at the end of the epoch 1 heavy operation, I can actually spread out all these regeneration operations throughout the epoch and get worst case log n overhead. Okay, so to sum up, if you start with linear size sorting circuits and smooth locally decodable codes with polynomial size code words and constant query complexity, you would get log n overhead for read-only ORAM. I'm wondering if I have time to talk about writes. How much do I have? 1 minute. Then no. So I'll do it in half a minute without the slides. So basically, the idea of the read-only ORAM, of the supporting writes, is to use a hierarchical structure, but instead of using a hash table in each level, we're going to use a read-only ORAM scheme. And there are two differences from hierarchical ORAM. So one is, you're accessing, every time you perform an operation, you're accessing each level. If you want little o of log n overhead, you have to squish the levels less than log n many levels, which means the ratio between consecutive levels is larger, which means you get higher overhead. This is why we get n to the epsilon write overhead. And the second thing, which I think is really nice, we're using a stronger primitive than in hierarchical ORAM, a read-only ORAM in the levels instead of hash tables. This means that reads are for free. So you don't count reads in the number of operations you perform towards reshuffle. So this is for people who really know ORAM. But if you don't, so let's go back. So what do we show? We show a barrier towards proving a lower bound. If you want to prove a login overhead lower bound for online read-only Oblivious RAM, this will imply a lower bound either on sorting circuits or on locally decodable codes. So forget we're in Oblivious, we're in lower bounds workshop. What does this mean? Do we have an online ORAM scheme? Can it exist with little of login overhead? So it depends again on your point of view. If you're optimistic, you say, sure, just come up with these sorting circuits, LDCs, we're done, right? Can go get coffee. If you're maybe more realistic or cautious, then you might say, okay, look, no way that we're going to be able to build these primitives, but we might have a different way, right? Think of a different way of constructing read-only or online ORAM scheme with little o of login overhead. Okay, that's it. Thanks.